We were talking earlier about free energy and equilibrium constants, and it turns out that those two things are related to cell potential. So here we have a nice little graphic here. And this is sort of a summary. For a spontaneous redox reaction, delta G will be negative, the cell potential will be positive, and the equilibrium constant will be greater than 1. And the opposite is true for non-spontaneous redox reactions. So there's a relationship going on here, and we're going to look at them. First, let's look at delta G and E. So potential difference, this E, potential difference is the difference of potential energy per unit charge. Now, I know that sounds a little redundant, potential difference and difference of potential energy. There's a difference between those two things. So E, the potential difference, is the potential energy difference, that's measured in joules, divided by the charge, which is measured in coulombs. Potential energy difference is the maximum work that can be done by that system. And charge is Q, charge. So we could take this and we can substitute in maximum work and Q, and we can get this equation here. So we could take that and rearrange it, solving for W max. So the maximum work done by the system is negative Q times the cell potential. Where did the negative come from? Does that bother you? When a system does work, is that positive or negative? It's negative. So I think of that like getting a massage or giving a massage. You know, you give a massage to someone, you are doing work on someone else. That's an outflow of energy from you. That's a more negative thing. Having someone give you a massage, that's a very positive thing, right? Unless you're ticklish and then you mess up the analogy. So the negative sign is put in there because of the definitions that we've done earlier. So the work done by the system is negative charge times the cell potential. Question? Well, here we're not specifying that it's being done by the system. It could be being done to the system. We're not specifying. Here we're specifying this is work done by the system.
We were talking about oxidation and reduction, and now we're talking about work.
Yes?
I'm missing the connection. What is work in relationship?
Work is a force exerted through a distance. And it is related to potential energy difference. So if you think about a piano hanging out a second floor window, if you cut the rope, what's the piano going to do? It's going to fall down. Is there a force involved in that? There is, the force of gravity. Is there a distance traveled?
Yes.
Yes. So by the physicist's definition, that is work. Why did the piano fall? In terms of potential energy, why did it fall? Because when it's hanging out the second floor window, it has higher potential energy, and when you let it go, it's going to go to lower potential energy. And when that happens, work is done. So here we've got things going in our electrochemistry, we've got things going from higher potential energy to lower potential energy. That difference in potential energy is work. Yeah, good question. Anybody else? We're skating into physics here. So that charge, Q, we can quantify that. And we do that using Faraday's constant. It's named after Michael Faraday. He did a lot of electrochemistry and stuff. So I have a son named Michael. Faraday's constant is abbreviated F. And what Faraday's constant is the charge in coulombs of 1 mole of electrons. And if you're interested, the charge in coulombs of 1 electron is given earlier in the chapter, and you could calculate what the charge in coulombs is of 1 mole of electrons. And this is what you come up with, 96,485 coulombs per mole electrons. You may end up memorizing that number because you use it frequently enough, but I would give you that on an exam. I wouldn't expect you to necessarily remember that. So that's how we quantify that charge in the chemical reaction. So then the total charge in the chemical reaction, Q, is equal to the number of moles of electrons times Faraday's constant. Because what would the units come out to be? Coulombs. Because N is in moles, so this equals moles of electrons times coulombs per mole. And so that gives us coulombs a unit of charge. This just allows us to get a number on this. So we've got that guy. So earlier we had the maximum work exerted by the system is equal to negative Q times the standard cell potential. If we substitute NF in for Q, we end up with this. The maximum work is equal to NF E. Now, a while ago, when we were talking about free energy, standard free energy is the maximum amount of work that can be done by a reaction. Delta G equals the maximum work. So we can take this and substitute in here, and we end up with this little gem. The change in free energy for the reaction equals minus NF standard cell potential. N is the moles of electrons. That comes from the stoichiometry of the equation. F is Faraday's constant, and Ecell is the standard cell potential that we just learned how to calculate. Any questions? Using tabulated electrode potentials. Calculate delta G0 for this reaction. Is it spontaneous? Well, we need our table. That's why I brought my book today. So what are the two things going on here? We got sodium going to sodium plus, right? Plus an electron. But there's some coefficients in there, aren't there? There's 2 sodium atoms going to 2 sodium ions, and then there would be 2 electrons. And then what's left? Well, we've got 2 H2O. I'm going to leave some space because there's probably going to be plus 2 electrons over there, huh? H2 and 2 OH minus. So in order for this is mass balanced, right? Yeah. In order to charge balance it, we need 2 negative charges on the other side. That's where those 2 electrons come in. To figure out the cell potential, I'm going to look up the electrode potential for each of these. One of them is written as an oxidation, one is a reduction. The reduction, I copy the E0 down. The oxidation, I change the sign. So H2O, I had a hard time finding this one earlier. It is here somewhere. H2O plus 2 electrons, E0 is minus 0.83 volts. The other one is written as an oxidation. As a reduction, the cell potential, or the electrode potential, is minus 2.71. So we flip this around, so it's now plus 2.71. This is written as an oxidation, and so I changed the sign on the electrode potential. To find the cell potential, I add these. So 2.71 minus 0.83 plus 1.88 volts. And that's Ecell standard. Just looking at that, would you predict that this is spontaneous? Yes. Okay, so now the question's asking us to calculate delta G. What's the equation? Minus NF
P prime cell.
0 cell. So the number of moles of electrons in this equation? 2. So that's 2 moles.
You would add them together.
There are 2 electrons, 2 moles of electrons being transferred.
Oh yeah, one second.
So earlier we mentioned that when we double this, this doesn't get doubled. This is where the doubling, this is where that factor comes in. Not in the cell potentials, but in delta G, the free energy. And then, let's see, 96,000, dang, I forgot it. 485. I remember the 85, I lost the 4. 485 coulombs per mole times the cell potential, which is plus 1.88 volts. Look at the units. Moles cancel. We're going to end up with Coulomb volts. What's a volt? It's a joule per coulomb. Joule per coulomb. And so then the coulombs cancel out. Yes, really. Did I do that one? I did that one. Oh, look, it's all written out right there. So that comes out to a really big number, which I'm going to put into kilojoules. And it's still pretty big. Minus 363 kilojoules. Is that a reasonable value for a delta G? Yeah, we were getting delta Gs that were in the hundreds of kilojoules. So that's reasonable. That's not per mole. That's for the reaction as written. That's for the reaction as written. And so we have a positive cell potential. We have a negative change in free energy. It's a spontaneous reaction. Any questions?
So if it was not spontaneous, was the change in G automatically be positive?
This would be positive and that would be negative. Is it possible for them both to be positive or both to be negative?
No.
No, it isn't. Because in this equation, there's a negative here. N can't be negative. F can't be negative. So whatever the sign on Ecell, delta G will have the opposite sign. Any other questions? What about cell potential and the equilibrium constant? I know, right? I decided there was no way I was going to be able to just write this out off the top of my head, so I wrote it, I typed it all out, which was also tedious, but at least it's going to be right. So we learned earlier that the change in free energy is equal to negative RT natural log of the equilibrium constant. That was the relationship between delta G and K. Well, we just showed that delta G is equal to negative NFE, right? So then these two things must be equal.
Yeah.
So that's what I did here, is I just put this one on the right side, this one on the left side. And then we can rearrange that, and I decided I probably could handle that. So we're going to solve for Ecell. I'm going to divide by negative F on both sides. Negative NF. So that cancels, this cancels, and the negative cancels. So Ecell, those cancel too, is RT over NF times the natural log of the equilibrium constant. Now, how did they get to this? Well, this is at 25 degrees Celsius. So at 25 degrees Celsius, T is 298. The gas constant is 8.314 joules per mole Kelvin. The Faraday constant is 96,485 coulombs per mole electrons, right? And N stays. And then they changed the natural log to base 10 log, and that factors in there also.
Okay.
There is a factor in there.
Okay.
Yeah, you can't just magically do that, but there is a relationship between natural log and base 10 log. And so what you come up with is this guy down here. So this is simpler because there's less math to do, but that's only at 25 degrees Celsius, which, most of the stuff we're going to do is at 25. So. Any questions?
So it's just saying that the relationship between Ecell and K is an equation.
Yes. There is a relationship, and it can be defined by an equation. So if you know the cell potential, you can figure out the equilibrium constant or vice versa.
Are there words that we can put with that?
The electrode cell potential, the standard cell potential is equal to 0.0592 volts divided by the number of moles of electrons times the base 10 log of the equilibrium constant. Those would be the words, I'm sorry.
Yeah, but okay, something that can tell me something.
Now, I can't think of anything now.
What does it mean? The cell potential is just equal to that.
It's just the relationship, and it's found mathematically. Yeah. Yeah, now we're going to calculate K using the standard cell potentials. And I forgot to superscript that plus, but we'll just leave it alone. So the equation, the cell potential is equal to 0.0592, I wrote this down, volts over N times the log of K. So we need the standard cell potential. So we've learned how to do that. So we've got 2 iron going to 2 Fe, 3 plus how many electrons? 6. And then the other is 6H plus 6 electrons going to 3H2. This is our oxidation, this is our reduction. If we look this up in the table, we see that this is the reduction, that is the equation for the standard hydrogen electrode. So E0 for that is 0 volts. This is written as an oxidation. We find it in the table as a reduction. And the standard potential is minus 0.036. Since we wrote it backwards, we'll change the sign to plus 0.036. The standard cell potential will be then plus 0.036 volts. What is N? Why 2? What does N represent? The moles of electrons. How many moles of electrons do we have? 6. Yeah. So N equals 6 moles of electrons. This is for the reaction as written. As written. So now we have to solve this for K. I generally prefer to rearrange equations first and then stick numbers in. So I'm going to take this little mess over here, and I'm going to get Ecell times N divided by 0.0592 volts is equal to the log of K, which tells me that the equilibrium constant is equal to 10 to the mess. 10 to the mess. That's the exponent. Right?
The next one, huh?
It is a hell of an exponent. And that's actually a 10, not a low. I don't want to do this on my cell phone calculator. I'm going to get out the real guy. So, depending on what type of calculator you use, it might be nice to have it rearranged and then you can just type it in. So I've got 0.036 times n is 6 divided by 0.0592. So I'm getting K is equal to 4.45 times 10 to the third. Looking at the cell potential, is this a spontaneous reaction? Yes. Just barely, but it is. It's a small number of volts, but it is positive. And our K down here, our K is greater than 1, which also suggests a positive, not positive, a spontaneous reaction, a reaction that favors the products as opposed to favoring the reactants. Any questions? We're going to stop there.